In this tutorial, we will cover the best practices for prioritizing fairness in AI systems. I'm Amit Deshpande from Microsoft Research, and I will cover the first half of the tutorial, and my colleague Amit Sharma will cover the rest. We thank Solon Barokas, Hannah Wallach, and Miro Dudik for their help in creating and critically reviewing these slides. We also acknowledge Microsoft Ether Fairness and Inclusiveness Working Group for contributing some of the content. The agenda. We will first tell you about the types of fairness-related harms, how to measure them, how to mitigate them. We will present a case study of fairness in a healthcare AI system, and we will end by pointing you to more resources so that you can do a similar exercise for an AI system of your choice. Challenges faced by AI systems have received a lot of attention in the media and have really highlighted how important it is to be aware of these dangers, consider the impacts, and take steps to mitigate them or even reconsider the original project. Some of these media stories have covered high stakes decisions where AI systems are used to allocate opportunities or resources in ways that can have significant negative impacts on people's lives. For example, many of you must have heard of the ProPublica investigation a few years ago, which showed that Compass, a widely used recidivism risk assessment tool, incorrectly scored black defendants as high risk more often than white defendants, while incorrectly scoring white defendants as low risk more often than black defendants. Other stories have involved much more mundane AI systems. For instance, researchers at Princeton found that translating "he is a nurse" and "she is a doctor" into Turkish, which is a genderless language, and then translating it back into English yields the stereotypical, and in this case also incorrect, "she is a nurse and he is a doctor." All right, so with that, let's move on to different types of fairness related harms. Broadly speaking, there are three main types of fairness related harms that can be caused by an AI system: allocation, quality of service, and representation harms. To explain each of these three types, I'm going to run through some illustrative examples, starting with the most well known type, allocation. But before I do that, I want to note that these types are not mutually exclusive. It's possible for a single AI system to exhibit more than one type of harm. And in fact, many of the examples that I will show you could have been used to illustrate one or more of the other types as well. First, allocation harms. As I said before, many media stories have focused on high stakes decisions where AI systems are used to allocate opportunities or resources in ways that can have significant negative impact on people's lives. For example, Amazon abandoned its automated hiring system after finding that it amplified the existing gender imbalance in the tech industry by withholding employment opportunities from women. Quality of service is all about whether a system works as well for one person as it does for another, even if no opportunities or resources are extended or withheld. For example, researchers found that three commercial gender classifiers had higher error rates for images of women with darker skin tones than for images of men with lighter skin tones. The same example actually also shows a third type of harm called representation harms. Like accessibility issues, these harms can raise questions about respect, dignity, and personhood. Imagine how a user might feel if a system repeatedly fails to recognize their voice, but easily recognizes those of their peers. AI systems can give rise to representation harms when they propagate invidious stereotypes, present members of certain groups in a demeaning manner, or under or overrepresent these groups' participation in different socially significant activities. For example, a few years ago, Google Photos infamously mislabeled an image of black people as gorillas. This mislabeling is harmful not just because the system made a mistake, but because it specifically applied a label that has a long history of being purposefully used to demean black people. I want to reiterate that the three types of harms are not mutually exclusive. A single system can exhibit more than one type of harm, as I have indicated here on this slide, and can even exhibit different harms for different groups of people too. Finally, fairness-related harms can have varying severities. For instance, unfairly denying someone bail is a more severe harm than labeling an image of a female doctor as nurse. But it's also important to remember that even relatively non-severe harms can make people feel alienated or singled out, and their cumulative impact can be extremely burdensome. It's also important to remember that groups intersect, and people within those intersections may be at risk of experiencing unique harms that might be obscured by considering only non intersected groups. Returning to the gender classification example that I mentioned earlier, error rates were significantly higher for images of women with darker skin tones than for images of women overall, or for images of people with darker skin tones overall. The researchers who conducted the study were only able to uncover these disparities by assessing system performance with respect to skin tone and gender at the same time. So, who is at risk of experiencing fairness related harms? Well, sometimes it is the people who will use or operate a system, but it can also be other stakeholders who are directly or indirectly affected by a system, either by choice or not. For example, in the case of a facial recognition system for workplace building access, the system operator is not the person whose face is being recognized, and thus not the person who is most immediately harmed if the system makes a mistake. I also want to emphasize that although media stories often focus on groups of people that are protected by anti discrimination laws, such as groups defined in terms of race, gender, age, or disability status, there are actually many different groups of people that we want our systems to treat fairly, and it's not always easy to identify the most relevant ones, which can even be specific to the domain or use case. For example, in the case of an automated essay grading system, whether someone is a native speaker of the language may be more relevant than their age or their disability status. How to measure fairness related harms? As an example, to measure the harms of a speech to text system, one must first consider what kind of harms may arise and which groups are likely to be harmed. A speech to text system used for personal note taking may have quality of service harms, or if it is used to evaluate call center employees, then it may have allocation harms. Minority groups and people with different voice accents are likely to be harmed by such a system. The choice of metric to quantify these harms depends on their types and severity. For voice transcription, accuracy of transcription for different groups of users could be a fairness metric to track with the goal of achieving similar accuracy for all groups or guaranteeing a minimum level of accuracy for all groups. For employee rating comparison, the distribution of call rating prediction errors in different groups of employees could be a fairness metric to track with the goal of achieving equal probability of positive predicted call rating in each group for the same call outcome. To summarize, measuring fairness related harms first requires understanding the types of harms that may occur and understanding which groups are likely to be affected. A fairness metric is ultimately an attempt to measure these harms. Group membership information is essential for this exercise. In case the group membership information is not available, we can see if group membership data can be collected or are there reasonable proxies for group membership. For example, geographic location or country can be a proxy for voice accents. Moreover, we need regular fairness evaluations as the model or data may change over time. That ends the first part of this tutorial. My colleague Amit Sharma will take over from here. Thank you.
Thanks, Amit Deshpande. I'm Amit Sharma, and I'll take you through the rest of this tutorial. So now that we have an understanding of fairness-related harms, we now would want to understand how to mitigate them. And the mitigation strategy depends on the source of the harm, right? So now to answer how to mitigate these harms, we first have to answer how do these harms arise. First, you might be thinking that it's due to some bad intentions. Actually, I want to explicitly emphasize that although there are many reasons why AI systems can behave unfairly, these reasons rarely include bad intentions on the part of the teams responsible for developing or deploying those systems. The actual causes are more complicated. And let's also get one more misconception out of the way. It is not the case that if you use only group information in your model, then unfairness can occur, and if you do not use group information, then there can be no unfairness. I want to emphasize that fairness-related harms can arise even if a model is not explicitly using the group membership of individuals. And in particular, to make sure I can cover different ways in which fairness-related harms can occur, I will give examples. In particular, I'll show three different ways in which harms can arise. Data sets, insufficient coverage, then the choice of the task in choosing the label, and then also the choice of the task in choosing the features and how to use them in a model. So first is due to the data sets. Some AI systems behave unfairly because of dataset characteristics, such as too few data points about some group of people. For example, let's go back to the example that Amit Deshpande had discussed earlier. And we saw that images of women with darker skin color had higher error rates, right? And the reason why these error rates for images of women with darker skin tones is higher is simply because there was not enough data in the data sets for this group of people. And so what happens is when the machine learning model is trying to learn the patterns, it simply does not have enough data for this group of women. And in some cases, the relative proportions of different groups of people in a data set may actually reflect reality. But the sampling strategy can still lead to insufficient data about groups that are smaller. And so this is something that needs to be mitigated. So how do you identify in your system if there's a harm due to insufficient coverage? So the first thing to do is very simple. You just analyze the number of data points for each group and then compare it with the measured harms for each group using an appropriate metric. If we do find groups with little data, but also they experience more harms than others, then it is most likely a case of insufficient coverage. In general, it can be mitigated by data collection. So we simply go ahead and collect more data for a certain group. But in practice, this is often very hard to do. And so we want to note that in many cases, it may not be practically possible to collect enough data for certain groups of people. In some cases, insufficient coverage is due to simply system design choices that shape data collection. A very simple example is click data on recommendation systems. So whenever a recommendation is shown to a person, we get whether they click or not. But if there are certain kinds of people for whom a recommendation was never shown, we would not have any data for them in our system. So in this case, mitigation is using randomization. So we can simply randomize a small fraction of the data, which means that we now decide to give recommendations at random, which means all groups of people get an equal chance to receive that recommendation. And then whatever system is built on top of that click data will also cover all groups of people. Another option is to use data from past A/B tests whenever they are available. Let's come to the second reason. The second reason why harms occur is mismatch in the task definition, specifically how the label is decided for a predictive model, let's say. Sometimes AI systems become unfair because of assumptions about what a particular data feature captures and how it relates to the system purpose. For example, this is a news article about a crime prediction system trained on an arrest data set. It relies on the assumption that the number of arrests in a neighborhood is a good proxy for the number of crimes committed there. Now, is that so? They are assuming that arrests can be used as the outcome variable as a proxy for the amount of crime. Now I'll let you guys think for a second about whether that may be true, but actually this is not true. In fact, this assumption fails to account for high rates of arrest without conviction or for over-policing in less affluent neighborhoods. Both of these can result in the arrest rate not being a good proxy for the crime rate. And so the resulting system may make inaccurate predictions that reflect historical policing practices rather than the occurrence of crime itself. So therefore, it is important to choose an appropriate label for the intended outcome. And I want to emphasize here that it's not about automatically collected labels or manually connected labels. Both can be problematic. Many times an automatically collected label, while convenient, does not capture the intended outcome. So let's take a simple example, time spent on a web page. This is a popular metric. It may be intrinsically higher for older people than younger people. Another variation it might have is that it may be higher for people with slower internet connections, which in turn may be correlated with demographics. So therefore, we need to be careful when thinking of this time spent on a web page as a proxy for relevance. Another type of data is user-collected labels. For example, this might be data that users provide on a particular platform. In general, this is considered more accurate, but here too one needs to be careful about any systematic processes that might cause missingness in the data. So as an example, consider labeling of fraud transactions by users or whether some content is labeled offensive on a website. Here again, presence or absence of labels might depend on the demographics or other characteristics of the users. At the same time, manual decisions or past decisions taken by people may also not capture the intended outcome. For example, promotion decisions at an organization may be historically biased against certain groups. And so whenever we are thinking of using these kinds of data as labels for a predictive model, we need to be careful that it is actually an appropriate label that represents the intended outcome. A third type in which harms can arise is the choice of features themselves, and more importantly than the choice of features, how that feature is used in the predictive model. A report found, for example, that Amazon's same-day delivery service, which uses a predictive model to decide whether to launch the service in a particular area, is less likely to be available in zip codes with predominantly black people. Now, how does this occur, right? The key issue here is that considering zip code as a feature and considering that as a measure of location may be problematic. In many cities, the zip codes are highly predictive of the racial composition according to the US Census data. And what might have happened is the model, which is based on some learning algorithm from the data, somehow learned to rank certain zip codes lower that also have a higher fraction of black people. So as I mentioned earlier, it's again probably not the intention of the algorithm designer, but due to choice of features and how it was used, we see this kind of fairness-related harm come up. So it's important to take precautions to use features and what features to use in a machine learning model and how to use them. The first point we want to emphasize here is that even with carefully collected data and labels, it is possible to cause fairness-related harms due to choice and use of features. So all three need to come together. Features that are correlated with group attributes can introduce fairness-related harms if not accounted for properly. And this kind of a problem is hard to mitigate, but one mitigation could be to critically check each feature and be transparent about the features used. Sometimes this may involve changing the feature. For example, one may choose segmenting based on metropolitan areas rather than the zip code. This ensures that the metropolitan areas are not that correlated with race, and so whatever model you're predicting would not pick up on those patterns. That said, sometimes it may be justifiable to use a feature correlated with group attributes. This is often the case where we want to use that feature to use it as a proxy to apply algorithmic mitigations or to measure fairness after deployment and to check how your model is performing. Finally, sometimes the issue with the task definitions are more fundamental. So it's not about having the right data set, the right label, the right features. It's sometimes more fundamental misunderstanding about what AI can and cannot do. Let me give you an extreme example here of what can go wrong. Actually, in 2016, a paper came out by a group of researchers who proposed training a facial analysis system that can predict who is going to predict a crime. Sorry, who is going to commit a crime based on the images of people's faces. This is extremely worrying for a whole lot of reasons and could lead to substantial harms for people who are misclassified. I hope it goes without saying that even with good intentions, this is a questionable system purpose. It's not something AI is actually capable of doing. And so just to summarize, the examples I showed you are by no means comprehensive, but I hope they've convinced you that there are many reasons why AI systems can behave unfairly. Sometimes AI systems behave unfairly because of societal biases that are reflected in the data sets used to train them, or because of other dataset characteristics, such as too few data points about some groups of people. So we saw that as insufficient coverage. And sometimes it's about the assumptions or the decisions made by teams, either explicitly or implicitly, through the AI development process. This could be the choice of label, the choice of objective, and in some cases, the very task that you chose to execute. Because there are so many reasons, and because these reasons are not mutually exclusive and actually tend to exacerbate each other, assessing and mitigating fairness-related harms are not things that can be treated as an afterthought. They need to be prioritized at every stage of the AI lifecycle, as shown in this slide. What have we learned so far? First, there are three main types of fairness-related harms: allocation, quality of service, and representation. Importantly, groups at risk of experiencing harms are context-dependent, and fairness-related harms can be introduced or propagated at every stage of the AI lifecycle. So to be specific, it includes task definition, data collection and pre-processing, model training, model evaluation, and finally model deployment and monitoring. Therefore, the assessment and mitigation, of course, has to take place at every stage. Let's now move to a case study to put these principles into practice, and we'll try to see how to assess and mitigate fairness-related harms in a real-world setting. This is based on a research article from Obermeyer et al., where they studied a widely used healthcare algorithm in the US. The goal of the algorithm is to support patients with the most severe health problems. So what this algorithm does is that it looks at past data of patients and tries to give them a risk score of how severe their health problems might be in the future, and that can be used by the healthcare system and hospitals to then prioritize those patients for healthcare. So how was this model trained? This model was trained using past medical records, and the outcome label used was the medical expenditure for the patient in the next year. Right? Now this can be thought of as a proxy for how severe their health condition is. The assumption is that more medical expenditure would be done for the patient as their health condition becomes more severe. So far so good, and the algorithm actually did not use race as a feature. Yet it turned out that the model favored healthier white people over sicker black people. Now this is clearly a case of fairness-related harm because for people who are sicker but belong to a specific group, which is black people, they are getting a lower risk score compared to healthier white people. The question that should come up is that how did this happen? And more importantly, how do we mitigate such fairness harms in systems like these? And especially because in healthcare, these kinds of fairness-related harms can be really severe. Let's ask the three questions that we learned during this tutorial. First, what kinds of harms might arise from a system that prioritizes care for people? Now, this system's prediction is used to decide who receives the prioritized care. Hence, this system is about allocation harms, right? Because it is allocating the healthcare services, If those are not done properly, they can lead to allocation related harms. Next, we will ask who may be likely to suffer these harms. So this would be racial and ethnic minorities and underrepresented groups in the data set. And especially because this algorithm was deployed in the US, you'll be looking at the race of people, which would be black versus white people. With these two questions, now we can answer the third question of how do we measure these harms. Since the algorithm aims to provide support to people with the most severe health problems, an appropriate question to ask is, across the racial groups, does the algorithm provide the people with the same health condition with the same score, right? So irrespective of which group do you belong to, if you have the same health condition, on average are the risk scores the same. And to instantiate this, there's one concrete measure that was used in the study is the calibration score. So it's simply the expected value of the health condition given that the model predicted a certain risk score. And what we want is that this expectation, this conditional expectation, should be the same across racial groups. However, it turned out that in the data that was studied, this metric was significantly different between black and white people. Now, once we have these three questions and we've understood that there was a fairness related harm, now our question to answer is, how did this harm arise? And to answer then this question, we look at the data and we find that the medical expenditure actually is not an appropriate proxy for severity of health condition. It turns out that for the same health condition, it was found that expenditure for white people was higher than black people in the collected data. Now, I want to pause and say that at this point, we may not be sure of what are the actual reasons, what are the societal biases and context that led to this finding. But from our purposes from building an AI system, this tells us that the problem that might be happening in this model is in choosing the right label, right? So the label that we chose, which was medical expenditure, in the real world, it is not an appropriate proxy for severity of the health condition. And this now gives us a nice base to now think about how to mitigate these harms, right? Because now that we know that a good probable reason for this is the choice of the label, it means that now we need to present a better label for the machine learning model to train on. One such thing could be to directly measure the severity of the health condition. So there are hospital codes available in the data and other kinds of inputs that can help us develop labels. So for example, you might think of the number of chronic conditions that flared up in a year for a patient. Another one could be emergency visits and hospitalizations in a year. One may also try to develop something aggregate, for example, a health condition score aggregated from different health events in a year. And again, it might not be clear which one actually measures the right outcome we are interested in, but having alternate labels like these and trying them out and perhaps also comparing across them can give us a better sense of what might be the right label that acts as a proxy. In fact, you can look at this link in the slide, which has a detailed case study on fairness in healthcare allocation decisions. So with that, we are at the last end of our tutorial. In the interest of time, I'll just point to some resources that I hope will be very useful for you to learn more and to explore fairness in AI systems. The first is an open source project from Microsoft to improve fairness of AI systems. This is a Python package called FairLearn. It provides metrics for assessing which groups are negatively impacted by a model. And it also provides algorithms for mitigating unfairness in a variety of AI tasks and along a variety of fairness definitions. There are also more learning resources that are linked on this slide. There are webinars that you can go through in more detail. And there are also more hands-on tutorial using FairLearn. And finally, the last link shows a list of responsible AI resources that you can browse to learn more. With that, thank you.